Welcome back to a very progressive dialogue in terms of deploying GPU-related use cases on our EKS Anywhere bare metal cluster with NVIDIA GPUs. In the previous blog and video, we had in fact seen how to deploy a Kubeflow on top of our EKS Anywhere bare metal cluster with GPUs. And then in doing so, we had also demonstrated a sample Jupyter notebook for training a TensorFlow job actually with Keras. Now we will move ahead from that point and start to kind of fathom complex topics like distributed training. And I don't want to emphasize or overemphasize on the need for distributed training. Time is money, and the faster you train, the better it is. But some of the interesting realities around how data sizes are exploding, or data set sizes are exploding, the model sizes are exploding. Hence, this distributed approach always works for a given range of use cases, I would say, right? Again, in the world of distributed training, you have concepts like data parallelism, model parallelism, and that's the reference terminologies that we generally keep hearing, right? But we have to kind of double click on this when it comes to individual frameworks in terms of how these things are implemented in frameworks like TensorFlow or PyTorch. And that's where today we will look at Kubeflow as that overlay orchestrator of sorts with a training operator. Okay, now training operator is a operator or is orchestrator of sorts, which orchestrates our distributed jobs actually in terms of creating these pods and containers which act as workers to actually run these distributed jobs. Okay, so we will have the same Kubeflow instance which is already deployed, and then Kubeflow we will deploy the training operator. In my case, it's already deployed, but I'll show you the command to do so. So you have the training operator, and then the training operator then creates these CRDs or custom resource definitions, which, like I said, for TensorFlow, it's called as TF job. For PyTorch, it's called as PyTorch job. So it's like a job of sorts which initiates depending upon how many distributed workers you need to run these, parallel processing for TensorFlow or PyTorch. Okay. Now, if the choice, like in this example, is going to be PyTorch, PyTorch has its own implementation techniques and nuances as to how do you achieve distributed training. To start with, at the tall order, you have asynchronous and synchronous form of doing what is called as data parallelism. Okay, model parallelism is a very different concept in terms of TensorFlow, and we are not going to talk about this. We will talk model parallelism as an example when we deal with PyTorch. We will stick with data parallelism to showcase this distributed training as an example. Like I said, there are two ways of doing it, asynchronous and synchronous, but it's all data parallelism. That's what we are, where the data set is sharded and split amongst the workers that will be involved in doing this, training actually. Now, since this is all happening on Kubernetes, essentially your workers are nothing but these container replicas of the same job actually, right? Which is doing this distributed training. And these containers are running or spun up through a concept called as, or a custom resource called as a TF job, which is provided by Kubeflow under the hood of training operator. Okay, so this is not your typical GUI of Kubeflow and you trying to build a UI based affair. It's just a YAML definition of deploying the training operator and then creating a YAML of sorts for a resource of the kind TF job. We will talk about these in specifics, but understand first that you have asynchronous and synchronous form of training within the TensorFlow framework. Actually, let me just detail this out in terms of the visual, and hopefully it helps you understand. Okay, so to deploy the training operator, this is just one command, and if your Kubeflow is up and running, this one command should take care of deploying the training operator as such, right? So I'm not going to get into the details of that. We've already applied that after we have done our previous Kubeflow deployment. Okay. Now, like I said, you have these two are standing in for the synchronous form of training where you don't have a in the context of Kubernetes, a separate parameter server container running there, a pod actually, right? Your workers are talking to each other. In this case, if you are doing this entire act on a single node with multiple GPUs, then it's typically called as a mirrored strategy. It's a synchronous form of strategy. If you have multiple nodes, and then you would like to use GPUs across these nodes as a clustered affair, then it's called as a multi-worker mirrored strategy. Okay. The third one, and these are both synchronous. The third one is a parameter server strategy, which to me personally, again, there are a lot of perspectives around, which is better. And I would say, given the use case and the scaling effort, I would say, I tend to lean more on the parameter server strategy, where you have one of the pod running as a parameter server, and you have a set of pods which are actually running across your nodes, doing these distributed runs, and then they continue to update the gradients actually on the parameter server without the need of individual pods of these job talking to each other, right? So it's like an asynchronous form. The workers don't depend on each other actually or wait for each other, and they continue to kind of upgrade their gradients and then download the weights and things like that. So this is what we are going to be looking at today. The parameter server as a pod, and then let's say you have this two pods which are going to be running the same or they are a part of the same distributed job, and they continue to, like I said, send and receive. Let's say that, right? I said once you deploy the training operator, then you have access to these custom resource definitions actually. So you can see that the Kubeflow training operator. Okay, so you start by obviously preparing your training code, right? Which is in this case a TensorFlow, where you actually write your entire training code, and in that training code you have to specify exactly which strategy are you going to be using. So in this case, since we are going to be using the asynchronous form of parameter strategy, the Docker image that I will provide for the training code already has that as a mention, and the entire procedure routines are written accordingly. Now, once you have created the Docker file, you then build what is called as a TF job. And then depending upon the variables set there in terms of the number of nodes, the number of GPUs, and blah, 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 when you deploy this particular training TF job, it basically will spin up one pod as a parameter server, and then depending upon how many workers, how many nodes you have, you will actually start building this, right? And that is where the entire interactions keep happening until the training job is completed. In the context of this example, we will see how the essence is, how do we actually maximize, right, things, and that's what we will see it in action, where once we deploy this, we will do multiple runs, scaling the replicas of our workers and seeing does it really make an impact to the throughput, which is actually made available to the entire job. That's, I would say, the moment of truth, right? Let's go ahead and look at the YAML. The YAML is plain and simple. Once you have the training operator deployed, which in my case I have deployed one single line and it should be done, you create the job as a TF job. Okay. And since this is an asynchronous form of training, you define the replica spec as the parameter server. This is a GPU, this is a CPU-based resource. You don't have to consume your GPUs for the parameter server. And then you decide upon what is your batch size, what is the model, and things like that. So our batch size, in this case, I have already experimented with different batch sizes. I saw that one GPU, typically in my case, I'm equipped with L40S. And, I'm saturated more or less for one GPU at about 256 as the batch size, right? Beyond that, I'm not getting more throughput actually, right? So 256 is what we will keep as the batch size. Model is the ResNet 50. And then number of GPUs I specify, right? And then the image, which is actually, in this case, a benchmarking image. available from Kubeflow. I'm going to use that one. And we will start by looking at one replica for the worker. So replica count will be 1. And then same batch size and model and things like that. Here, the number of GPUs that we will mention is, we will keep changing this count as we iteratively do some benchmarking. And then we specify the limits in terms of, the GPU requests and all. Now, let's take this particular YAML. Okay, so we will start with one replica of our parameter server. Like I said, let's keep the batch size as 256, since that's the saturation point for this benchmarking with one GPU. CPU, we'll keep it as 1. Replicas for workers, we will start as 1. Okay. And the number of GPUs also as 1. What else there is to it? Nothing else. I mean, so if you were to do this on a manual basis, typically what you end up in doing is create instances through Jupyter notebooks, right? You create, for each worker, you would create a separate notebook and run this particular training code on each of them, and then induce these variables of which is the parameter server and all those manually. All that is kind of ridiculed through this CRD called as TF job. Once you do this TF job, the induction of these variables as to, the parameter server creation, the worker creation, expansion of the creation, and all that is automatically taken care of, right? So no need to kind of do this manually. Just go ahead, deploy the training operator. Let me go back to my terminal here. And this is our kubectl get nodes -o wide. This is our EKS anywhere bare metal cluster, the same cluster we are working with, one control plane, 2 worker nodes. Again, we do have our kubectl get pods -n GPU operator. This is loaded with the GPU, NVIDIA GPU operator is running, Kubeflow is running. So everything continues from the previous example, right? So I'm not going to kind of delve into that again, right? What we are going to now do is take this. I've taken this. Okay. Let's start by saying kubectl get TF job. So you can see that there is no TensorFlow job running in the default namespace as of now. Likewise, correspondingly, if I say kubectl get pods, there are no resources in the default namespace. So let's go ahead, deploy this TF job with one parameter server, one worker with one GPU as the use case, right? The moment we do this, for a first time run, obviously the Docker image will be downloaded from your registry, so it might take time. I've already done this on the same cluster, so it's the images are already present on the node, so the act will be quicker. So you can see that the kubectl get TF job, the name of the job is TF smoke GPU, the state is running, and on account of this particular job, we will see that the pods should have spun up. So you can see one pod for the parameter server as indicated by PS0, and one pod for the worker as indicated in our job template, which is one replica. Okay. Now, if I say kubectl get our logs and the logs of our worker, you will see that it is running the command. The launcher has started. The command is basically what we had presented as the args here. Okay, so on the worker, our args were these. Okay, the model, the batch. Oh, did I not change the batch size? Okay, let's do this. Let me kill this job. kubectl get TF job. kubectl, it'll take a couple of minutes more. It's good actually to understand these from a practical nuance. So let me delete this particular job. I don't want to kind of spend time in going from 32 batch size to 256. So I'll go ahead and reapply this particular example, taking batch size as 256. Okay, I made the change here, but I forgot to make the change here. Okay. So let's take this example again. Okay, kubectl get pods. Okay, they are terminating. Let's give it a minute or so. Let the job terminate. Okay, so the pods are gone. The job is deleted. I will go ahead and reapply this particular template. Now this time the batch size is 256. Sorry about that. So kubectl get pods. Both the parameter server and the worker pods are running. kubectl logs the GPU worker 0. You can see that the the device is already found with the properties NVIDIA L40S. Since we are working with one GPU, and this is what it is basically, right? Plus, it has already started, the benchmarks.py script. So what will happen is basically we will give it some time, as there will be a GPU warm-up phase, a cleanup phase, and all that, and then it will start running the benchmarking, and you will progressively see things changing actually. Okay, so let's give it some time, and as the job starts yielding result, I will continue to share and observe. Okay, so we can see after a brief run, let me repeat the logs command again. So once the the entire job starts, basically, given everything else, we can actually see the most important piece of our benchmarking results. And the total images per second, which is the throughput, let's say that, is coming up to 321.89 or whatever, right? So in this case, this is not really a distributed training, right? We have only one GPU used as a single replica, right? Now what we will do is we will actually step up the effort in utilizing this in the form of two GPUs, okay? And we will see how things change, if they change, and do we get a better throughput actually in terms of doing so. Okay, so what we will do is, let me first clear the terminal and kubectl delete tf job tf smoke GPU. Okay, let's see if the pods are gone. They are indeed terminating. Let them terminate. Okay, so the previous pods are terminated. Everything is clean, back to square one. Now, what we will do is we will redeploy the same YAML, but in this case, the PS replica is going to be 1 itself. The batch size is 256. We will keep the the number of GPUs now, okay, as 2. Okay, so we do have one replica and 2 GPUs. Let's update it on the parameter server. The parameter server is not using a GPU per se, but I have to start the job with that count on both the parameter server and the, so we can see, right, the device GPU here and device CPU on the parameter server. So num GPUs is 2 here, num GPUs is 2, batch size is 256, everything else stays. The limits have to be updated to 2 also. Okay, so I'm just making sure that we have everything intact now. Replica is 1, so we will have one replica. Or, yeah, I mean, let's try out this one. In the next example, we will anyway do a multi-node affair actually. Okay, we are now going to deploy this as a YAML. Okay, let's say kubectl get tf job and kubectl get pods. So we can see that, oh, yeah, this is good. So we do have now one parameter server and one worker. But in this case, the difference is that this one worker is going to be working with 2 GPUs as opposed to the previous example, which is 1 GPU. So let's look at the logs. So we can see that, 0 and 1, both GPU 0 and GPU 1 both have been detected here. So this is good. Okay. Uh, you can also see here found device 0, found device 1. Okay, so we'll let the job run as such, and I will resume once this particular job is completed. And then we'll do some quick observations there, right, in terms of a comparative analysis. Okay, so as intended and as we observed, let me just clear the log and just rerun the log. Okay, so this is what the throughput is now achieved. We have a use case now of distributing our workload of training over a single replica, single node, but across two GPUs actually on the same node as such, right? And last time we saw this was 320 something, and now the throughput that has been achieved is almost doubled actually, right? Which is actually a good thing, right? Given that this is still across, a single node because it's a single pod, right? You CTL get pods. It's still a single pod, which means it's still running on a single node with two GPUs. Now we will actually shift gear to actually doing this across the two nodes, which will give us a total yield of 4 GPUs, right? And that's what essentially the main intent would be in most use cases where you have multiple nodes in a Kubernetes cluster. And how can you actually leverage the entire, base of the cluster, right? Maybe whatever the count of your GPUs is. So let's delete our TF job, kubectl get delete TF job, tf-smoke-GPU. Let's see if the pods are deleted. They are being terminated. While this happens, let's now update our YAML to reflect the new intended capacity with number of GPUs as 2. Yeah, this should be okay. It'll start with 2 GPUs per node, but the number of replicas now go to 2. So 2 GPUs per replica, right? So this is good. The number of replicas 2, batch size still remains as 256. Number of GPUs per replica will be 2. Everything else stays the same. So the only change that we have now done is increased our replica count from 1 to 2, and that too on the workers actually, not on the parameters. So let's clear this. Let's see if our pods are gone. Okay, indeed. Let's paste this YAML. So this is the third use case. We moved from 1 replica, 1 GPU to 1 replica, 2 GPUs, and now to 2 replicas and 2 GPUs. So firstly, let's validate. Okay, let's validate if these both pods are running across. They have to, but let's just validate that they are indeed running them across 2 separate nodes, right? So that we can leverage the. So you can see that worker 0 is running on PRDW-02, and the next pod is running on 03. Okay, so 2 pods, 2 GPUs each, 2 nodes, right? Let's look at the logs of the worker 0. Okay, same thing. We can see that found device 0 and found device 1, both are L40S. Now let's look at the worker 1, which is running on a different node. So found device 0, found device 1, and both are L40S, right? So now the whatever warm-up phase will happen and the processing will start. We'll come back once, it's and do a quick set of observations. Okay, so now this is completed, and we can clearly see on individual node, the images per second is around 644, but when you see the aggregate throughput, as reported through the convergence, we can very clearly see that from the first use case where we had around 320 odd as the throughput, to with one replica, one GPU, to one replica, two GPUs, where we had around 600 plus as the throughput. We've now quadrupled throughput to about 1256, right? In essence, this is a massive jump. But again, this is expected, right? In essence, what we're trying to, or in summary, what we've just observed, how we can, given a data set, and a certain batch size and all that, how we can increase the footprint of our training job if you have the underlying capacity available in terms of multiple nodes and multiple GPUs, and how we can accelerate our training process by streamlining a bigger footprint actually of processing, right? So I would say that at this point, this is a done example, and I hope you found it insightful. At the end of the day, we actually worked with a concept called as TF job in the context of a training operator in Kubeflow, which gives us the orchestrated way of actually creating TensorFlow jobs for distributed training, right? So till next time, thank you.